Hello, I am Orit, Assistant Professor from Gary Memorial Institute of Technology. In the last lecture, we are construct a equation for the distribution function for the FD statistics. Okay. In today's lecture, we try to evaluate what is Fermi energy. So, in the last lecture, we already construct the Fermi distribution function. Okay. Now, we take a condition for the calculating of the Fermi energy at T is equal to 0 Kelvin. We have we have a distribution function Fe is equal to 1 by exponential over E minus Ef by kT plus 1. Ef is the Fermi energy, K is a Boltzmann constant, T is a temperature, E is a arbitrary energy. Okay, now we try to develop what is Ef. Okay, so at 0 degree Kelvin, if you put the temperature, if you put the whole system is a 0 degree Kelvin temperature, what will be happen? The distribution function is become 1 when Ei is greater than Ef. Clear? And it is become 0 when Ei less than F. So thus we try to prove this one. Okay, thus at the absolute 0 temperature, the function of Ei is a step function. Okay, so if the graphical representation of this function is like that, if you plot distribution function is here, Ef, where T is equal to 0 degree Kelvin. T is equal to 0 degree Kelvin, and it is like this. 0 degree Kelvin. Okay, is that how it can be proved? By that, as the temperature increases, the occupation index FEI changes from 1 to 0. So now at all non-zero temperature, that means when the value of the T is always greater than the 0 degree, that means T is always greater than 0. At T is always greater than 0, temperature at E is equal to EF. For the all non-zero temperature, as well as when the Fermi energy and the arbitrary energy is become equal, if you put the function 1 by e to the power EF minus EF by KT plus 1, it is become 1 by e to the power 0 plus 1 is equal to 1 by 1 plus 1 is equal to 1 by 2 is represent 0.5. So from this graph we can show that at any arbitrary non-zero temperature, the at when the value of the E is become EF, this whole distribution function represent half. That means at any non-zero temperature, when the Fermi energy become the arbitrary energy is equal to arbitrary energy, the whole distribution function or the whole particle the probability, the occupancy of the all particle is 50%. That means thus Fermi level is that energy level for the occupation of probability at T greater than 0 degrees temperature is always half or 50% of the quantum state. That means in the any non-zero temperature, the occupancy of the particle is 50% of the quantum state. That means the whole number of particle may be always be occupy the half quantum state, minimum half quantum state at non-zero temperature. And when the energy of the particle is become equal to the Fermi energy, then obviously the whole number of particle occupy the 50% of the quantum state. So that graph, the second graph is represent the at the 0 degree non-zero temperature, at non-zero temperature the whole number of particle the whole number of particle occupy the 50% of quantum state. Is it clear for everyone? Okay. So from the calculation we get at the temperature non-zero temperature when E is becoming EF, it is represent the half probability. If you draw the whole graph very specifically, very broadly actually, it is a one step down. That's why such type of function is also known as step function. Okay, so at fe e at e is equal to ef is that point, the maximum probability is half when e is become ef. Okay, this is the 0.1, this is the 0.5, and this is 0.0 for the probability distribution. That means at e is equal to ef, the maximum probability is 50% or 0.5. At e is less than ef, we get the maximum probability 1, and at that point e is greater than ef, the maximum probability is 0. That means when the particle have a energy is less than the Fermi energy, the occupation of the quantum state by the particle is 100%. When the energy of the particle and the Fermi energy is become equal, the occupancy by the particles in the quantum state is 50%. But when the particle energy is much greater than the Fermi energy, the occupation of the quantum state is become 0. That means no one particle in the system cannot occupy by the any energy level. That means such type of particle is now free particle. Just like example, when the electrons are flowing through a wire, that means what is responsible for the flowing of current? The free electrons. That means in the system of the wire, the energy of the electrons, which electrons are responsible for the flowing of current, which electrons are actually have a energy is greater than the Fermi energy of this system. That's why those electrons are freely available in this system, and this is the condition for the free electrons. This is the condition for the all electrons is occupied by its quantum state or is every specific orbit. Is it clear for everyone? Okay, so next, in the next derivation, we try to determine of Fermi level of electron gas or metal. Why electrons, gas and metal? Because in a metal, we all know that in a metal the free electrons are easily available. That's why such type of system is known as the such type of system we consider as a system is full with the electrons gas, and the particle of the electrons is represented as a gas particle in that system. Okay, if the energy levels are closely spaced, the number of particles with energy between E and E plus dE. So from the distribution function we all know that N E by GE is equal to FE. Clear? we rewrite here Ne Fe Ge, multiply the both side with De, Fe Ge De, then the total number of electrons Ne 0 to infinity, the energy level from 0 to infinity, it is NED. So 0 to infinity GE FE DE. Clear? Ne 0 to infinity 8 root 2 by pi v n to the power 3 by 2 e to the power half of by h cube 1 by e to the power e minus ef by kt plus 1 into de. This is the density of state. We have already construct this function in a density of state lecture. Please, if anyone doesn't know about the what is that, please see that lecture, and obviously the it is G, density of state, and this is the distribution function 1 by e exponential e minus ef by kt plus 1. Put the value is here and here. Clear? This is the density of state. It is actually 4 root 2 pi v m to the power 3 by 2 e to the power root by h cube distribution function for the ordinary particle. For the electrons, because the electrons obey the Pauli exclusion principle, that means one quantum state or one energy level can be occupied by the two electrons with opposite spin. That's why 2 is multiplied with this whole function, it is become 8 root 2 pi v m to the power 3 by 2 e to the power half by h cube. We already construct this function in a density of state lecture. Okay, now try to integrate this equation. N E 8 constant, root 2 constant, pi constant, v constant, volume is always be constant, mass is constant, Planck constant is constant, 0 to infinity root e de by e to the power e minus ef by kt plus 1. So this is the energy distribution for free electrons. Okay, for free electrons. Now try to calculate the total number of electrons at that system by calculating the integration at 0 degree E as at T, it is absolute temperature. The Fe is become 0 Fe when E is greater than Ef, and it is become 1 E is greater than EF. Clear? So this is, so we can written here like that: V m to the power 3 by 2 by h cube 0 to EF, because the energy of the electrons is does not overlap the Fermi energy. The energy of that electrons in between that system must be in between the 0 to EF. This is the condition for the distribution function. So the integration limit is become 0 to EF. dE, and we all know that at E minus EF by KT plus 1. Okay, again for the condition E equal to 1, E greater than EF, we chosen this condition. So now n is become 8 root 2 pi V m to the power 3 by 2 by h cube 0 to EF e to the power half dE, because the distribution function Fe is become 1. So we put the value of the e to the power E minus EF by KT plus 1 is equal to 1. N is equal to 8 root 2 pi V to the power m 3 by 2 h cube EF to the power 3 by 2 by 3 by 2. So EF to the power 3 by 2, just simplify this equation, 3 h cube n by 16 root 2 pi V m to the power 3 by 2. Just cross multiple to each of the equation. So EF is equal to h cube 3h cube by n 16 root 2 pi V m to the power 3 by 2 whole to the power 2 by 3. H square by 8m 3n by pi V by 2 by 3 EF. Okay, or EF is equal to h square by 8m 3n0 by pi 2 by 3, where n by V is represented by n0, the number density per unit volume, or written here n0 is the density of free electron. So EF is equal to h square by 8m 3n0 by pi 2 by 3. This is the Fermi energy of the free electrons in metal or any type of electrons gas, where in the system the electrons are freely available. In that system the Fermi energy of that system always be obeyed by this equation. So this is the Fermi energy at 0 degree Kelvin. If the temperature is not 0 degree Kelvin, then EF at T is equal to EF 0 1 minus pi square by 12 k square t square by ef square 0 0. This is the Fermi energy for the non-zero temperature. And this equation is known as Sommerfeld equation. It is given by the Sommerfeld, that's why this equation is known as Sommerfeld equation. Okay, thank you. So today we are study first what is Fermi energy, what is the Fermi energy, and what is the condition of the occupancy of the electrons and specific temperature or the energy level. We can see that at absolute temperature, when the particle energy is equal to the Fermi energy, the occupancy of the particle, the half of the particle is occupied by the quantum state and the half of the particle is freely available. At E is greater than Ef, we can see that all electrons in the system is occupied by the every quantum state. And when the E is greater than, the particle energy is greater than Fermi energy, the no one electrons is occupied by the any quantum state. That means whole system is freely available. So that means the all electrons, all particles or all gas particles are free in that system. In the next, we try to determine the Fermi energy level for the metal or electrons gas. Why? The metal have a free electrons are available in this material. That means we consider a metal as a system with full of free electrons, and electrons in the system is, now we consider the electrons is behave like a gas. So that's why we chosen the distribution function Ni by Gi is equal to Fi. We put Ni is equal to Fe into G into dE. We multiply the d in the both side, then try to integrate over this. Then we put the distribution function is 1 by E minus Ef kt plus 1, and the quantum state or density of state is 8 by 2 by pi m to the 3 by 2 it is a root by h cube. And we already construct this function Ge is equal to this one in a density of state lecture or quantum state lecture. Then we try to calculate the energy of the Fermi energy of the system. Then we consider the two conditions. In the first consideration, the temperature is 0. So in the 0 degree temperature, the energy of the particle in the system always be in between 0 to Ef. So we consider the limit of this integral from 0 to infinity to 0 to Ef, because in the system always the electron get the energy from 0 to Ef at T degrees temperature. When the Ef is become E, so the distribution function becomes 1. So we put the value is distribution function is equal to 1. So then we just simplify the just integrate this function and then simplify this equation, we get this one. So from this one, this is the Fermi energy of the system at 0 degree Kelvin, when the energy of the particle is always greater than the Fermi energy. And we all know that when the electrons have a greater energy than the Fermi energy, then no one electrons occupied by the any quantum state. That means whole number of electrons is now freely available. Okay, so in this lecture we calculate the Fermi energy. Okay, so in the next lecture we try to calculate the average electron energy at average energy of the system. This is the Fermi energy at the 0 degree Kelvin. So we can in the next lecture we try to calculate the average energy of the system. Okay, thank you. Hello, I am Audit, Assistant Professor of the Gargi Institute of Technology. in the now we are study in our lecture series the what is lecture series statistical mechanics. In the last lecture I already evaluate the Fermi energy of the free electrons. Now in this lecture I try to evaluate the average electron energy at absolute zero temperature for electron gas or metal. So the average energy, obviously the limit of the electrons energy is 0 to EF. So suppose E is the energy of the particle, each particle, n is the total number of particle. So this is the average energy of the system, or so actually this is the total energy of the system, total energy 0 to EF GE FE DE, because we all know that NE is equal to GE FE. Now 0 to EF E, put the value of the density of state 8 root 2 pi V m to the power 3 by 2 root E by h cube, and the distribution function we put it FE DE. Now 8 root 2 pi V m to the power 3 by 2 by h cube 0 to EF e to the power 1 plus e to the power half, it is become e to the power 3 by 2 FE DE. So 8 root 2 pi V to the power m to the power 3 by 2 by h cube 0 to EF e to the power 3 by 2 DE at t is equal to 0k, at t is equal to 0k FE is become 1. So this is a U0. We try to calculate the total energy 8 root 2 pi by V m to the power 3 by 2 by h cube 2 by 5 EF, it is for the 0 degree temperature, by 5 by 2. We can rewrite this equation n EF to the power 0 U0, where EF0 we have already know that EF0 is the h square by 8m n 3n by pi V by 2 by 3. If you put the value of the EF is here, then we get U0 is equal to 3 by 5 and EF is 0. So this is the total energy of the system, and the average energy must be U0 by n. The total energy per particle is 3 by 5 EF 0. So the average energy of the system is 3 by 2 EF. And also if you compare this average energy of the particle with the classical one, classically the average energy at temperature T is always 3 by 2 kT. So from this one we can easily evaluate that EF is equal to KT. It is for the classical system, this is for the quantum system. Clear? So it is the end of the video. So in this lecture we have calculated the total energy of the system and the average energy of the system. Thank you. Okay. Next, in the next lecture we try to construct a equation of Planck's radiation law. This is the one of the example of the Bose-Einstein statistics. So in the next lecture in this lecture we try to solve some application of the FD statistics, because the electrons, gas or the metal is an application of the FD statistics. So in the next lecture we try to construct the concept for the B statistics in the application of the Bose-Einstein statistics by the Planck's radiation law, Stephens-Boltzmann law, Wien's law, Rayleigh-Jeans law, etc. Okay. So today it is the end of the lecture. Thank you. Have a good day. Be in a home. Be safe. Thank you.